Okay, so welcome to the video recitation, the last one of the semester. Hope you have learned a lot and good luck on your test that's coming up. Let's get started with chapter 14, question 77. So this one is: a thirsty nurse cools a 2-liter bottle of a soft drink, mostly water, by pouring it into a large aluminum mug of mass 0.257 kilograms and adding 0.120 kilograms of ice initially at negative 15.0 degrees Celsius. If the soft drink and mug are initially at 20 degrees Celsius, what is the final temperature of the system, assuming no heat is lost? Okay, so you've got the drink, which is mostly water, so we'll use the specific heat of water. Got the temperature, amount, all this stuff. So it's asking about the final temperature of the system. So it's asking for Q, which means we'll calculate the Q for the drink, the mug, and the ice, and then sum those, and that will be the total Q. But remember that if the system has no heat lost, then the sum of the Q's is going to equal to 0, and then we'll use that to calculate the temperature. So first, you write down what you have. Then you have the specific heats of the different items. That's going to be found on table 14.3. In the test, you'll be given that. And then, final temperature of the system. So the Q of the drink, MC delta T, you've got M is equal to, so because they gave us 2.00 liters, then we have to convert that into mass. And so this fancy P thing is supposed to be density. So you know that the mass equals the density times the volume. The density of water is 1,000 kilograms per meters cubed times the volume, which is, 2 liters is going to equal to 0.002 meters cubed. So that's just a conversion there. So you calculate that, gives you 2 kilograms, and then you apply it to this equation here. So 2 kilograms times the specific heat of water times the change in temperature, 20 minus T, it's going to give you this number here. Then you move on to the Q of mug. And you've got the mass of the mug times the specific heat of aluminum times the change in temperature. This is your final answer there. Then you have the ice. So because this has a phase change, then you have to calculate the, MC delta T to the phase change, which is going to be equal to 0 degrees Celsius. And then you calculate the heat of fusion. You can find that on table 14.4, but in the test, it'll also be given in the problem. So then that's going to be, the mass times the heat of fusion. In this case, it's 334,000. And then you'll add that to the mass times, now that it's water, because the phase change is already completed, then use the specific heat of water here, and then the final temperature minus 0 degrees Celsius, and you calculate all of that, and that gives you this number here. So at that point, you want to sum these underlined values that you got for each of the individual parts of Q. You know that the sum of Q equals 0, like I said before, and then you basically move all of the T's to one side here, and then move all the other numbers to the other side. And you'll, sum these things, sum these things, take this divided by this, as you can see here, and that'll give you 14.1 degrees Celsius. So that's that problem. Then moving on to chapter 15, question 52. Okay, here we are. A volume of air, assumed to be an ideal gas, is first cooled without changing its volume and then expanded without changing its pressure, as shown by the path ABC in this figure here. A, how does the final temperature of the gas compare to its initial temperature? So first we'll look at that, and then we'll go back. So T final versus T initial. Well, we know that pressure times volume equals nRT, where nRT, N and R are constants. So the only things that are changing is the pressure and volume and temperature. Right, so the initial pressure, as we can see here, you can look at that, but the initial pressure is 3 times 10 to the 5. Initial volume is 0.02. So then you calculate that, and that's going to equal to 6,000 joules. Then you calculate at C, so the pressure this time 1 times 10 to the 5 times the volume at this point, which is 0.06, and that also equals 6,000 joules, which means that since N and R are constants, then the T final and the T initial are going to be the same because these numbers are the same. So how do they compare? They're equal. Okay, so moving on to B. How much heat does the air exchange with its surroundings during the process ABC? Does the air absorb heat or release heat during this process? Explain. All right, so for an ideal gas, then the change in U depends only on temperature, which we can see that the change in temperature is equal to 0. So that's not supposed to be there. There we go. Which means, if you look at the delta U, then that equals to the Q minus the work. So we can calculate the work and find out Q, because if delta U doesn't change at all, then that means that this Q equals to W, as we see here. So if you calculate work, you calculate Q, and that's going to be your answer. So for A, B, right, for when you're keeping constant volume, we calculate that Q. Since the volume doesn't change, then the work is going to equal to 0. Right, because work has to have some kind of distance involved, and in this case, that would be through volume changing. Then you calculate through B to C, here to here, where the pressure is constant. So you use the equation work equals pressure times the change in volume. Calculate that, and that's going to equal to 4,000 joules. And then you sum the two, and that's going to equal the total work. So work of ABC equals work of AB plus work of BC, which equals 0 plus 4,000. So it's 4,000 joules that is going into the gas. You see this positive here. Right, so the system is gaining 4,000 joules, which means that the air pours the heat into the system. And then we'll move on to question C, which is, if the air instead expands from state A to state C by the straight line path shown, how much heat does it exchange with its surroundings? So now it's saying if it just goes from here to here, what's the Q? Right, so the Q is still going to equal to the work. And work in this case is going to be calculated by the area under the dotted line. So since it's a triangle, then it's going to be half of this distance here, which is going to be 2.0 times 10 to the 5 here, and times this distance right here, which is going to be 0.04. So then put that in, and that equals 8,000 joules of heat into the system, right? Still, the heat is going into the system, but now it is double what it would have been if you had gone in straight lines, right? Because the area here is bigger than the area here. All right, so moving on to the next question. Oops. Still chapter 15, now looking at question 70. Right here. Helium gas expands slowly to twice its original volume, doing 300 joules of work in the process. Find the heat added to the gas and the change in the internal energy of the gas if the process is A, isothermal, and B, adiabatic. Not exactly sure how to say that, but adiabatic. Okay, so A, isothermal. So it's asking, find the heat added to the gas and the change of internal energy. So delta U and the delta Q, or Q. A, isothermal, means constant temperature. So delta U equals N CV delta T, which, constant temperature, so delta U is going to equal 0. So then again, you see that delta U equals Q minus W, Q equals W, W equals 300 joules, as we were told before here, which means that Q is going to equal to 300 joules of heat going into the gas. Adiabatic means that the Q is going to equal to 0, so no heat is entered or exiting the system, right? So delta U is going to equal to Q minus W. So if Q equals 0 here, then the delta U is going to equal to 300 joules. Yep. And of course, Q is going to equal to 0. That's all for that question. Then we will move on to 16.13. Let's see here. Okay. 16.13 here. Okay. A freezer has a coefficient of performance 2.40. The freezer is to convert 1.80 kilograms of water at 25.0 degrees Celsius to the same mass of ice at -5 degrees Celsius in 1 hour. What amount of heat must be removed from the water to convert it to ice at the final temperature? That's A. So we'll look at A first. Yeah, you can see that. So the performance coefficient K is going to equal to the QC, so the heat that is taken from the cold scenario by the fridge and expelled into the hot system, the hot area. Right, so QC divided by absolute value of work, and they gave us equals 2.40, and we'll use that later. But first, A is asking for water to ice. This is the mass. Delta T is 25 degrees Celsius to -5 degrees Celsius. So A. Q is going to be the heat of that transition, and like before, it'll be the heat of the different aspects of the transition. So mass times C times delta T to the freezing point, right? So from 0 degrees Celsius is the freezing point minus 25 degrees Celsius, the original. So that's where this number comes from. And then you'll minus, because over here, right, we're looking at the sum. So this here is going to equal a negative because of this number, this sign here. And the total heat is going to be all of them combined, right? And this one is negative here. So we're going to minus this one so that they're all the same sign, and we get the total number here. Yeah, so be careful that this sign matches whatever sign these two have. And these two should have the same sign. Will have the same sign. Okay, so minus mass times the heat of freezing. Sorry, the C of freezing. And then mass times C times delta T, of course again, where it's going to negative 5 degrees Celsius. Then you calculate those out, and then you have negative 8.08 times 10 to the 5 joules of heat is removed from the water, right? So this negative here means that it's going to be pulled out of the water. That's the Q, right? Now, if you look at it from the fridge's perspective, the right here, negative is because it's looking at it from the water. You know, it's taking the heat from the water. But from the fridge, it's pulling the heat from the water. So it's positive here. So that's something to remember here, that QC is going to be positive from the fridge's perspective. Yeah. So that's A. And then we'll move on to part B. How much electrical energy is consumed by the freezer during this hour? So what is the work, right? So here, I messed that up here. So B is what is work, and C is what is QH. All right, so work, right, like we said before, the absolute value of work, if you just rearrange this, it's going to equal to the QC, so the positive value of this, right, because it's going to be positive, divided by K, the coefficient, performance coefficient, and then you'll get that it's going, the absolute value is 3.37 times 10 to the 5, but you're going to take the negative value of that for work, because the work is done on the fridge, right here, and so the work is going to be less than 0. Yes. And then you move on to question C. How much wasted heat is rejected to the room in which the freezer sits? So Q of H, what's the heat that's expelled from the fridge? Q of H is going to equal to W minus QC, because work equals QH minus QC here. So you just rearrange this equation here, and then you plug in the values, right? So work, we just calculated that. It's this minus QC. This is going to equal to this number right here. So that is 16.13, chapter 16, question 13, and then moving on to question 20. And you see that? Okay. A Carnot freezer that runs on electricity removes heat from a freezer compartment, which is at negative 10 degrees Celsius, and expels it into the room at 20 degrees Celsius. You put an ice cube tray containing 375 grams of water at 18 degrees Celsius into the freezer. A, what's the coefficient of performance on this freezer? A, K equals what? In the Carnot equation, then, right. So let's go back a couple pages here. Right, so if you look at the Carnot equation, then you see that the efficiency is 1 minus Tc over Th. If you look at the heat equation over here, the efficiency is 1 minus Qc over Qh. Right, so in the Carnot equation, Qc is is comparable to Tc, and Qh is comparable to Th. So we're gonna, we see that here. And then you'll just kind of put that into this equation here and use this as Tc over Th minus Tc and find the efficiency that way. Yeah. So Tc, this, and then you convert it. You have to convert it to kelvins first before you do this. So just remember that. So you've got, the negative 10 degrees Celsius divided by the 20 degrees Celsius minus the negative 10 degrees Celsius. And that's all in Kelvin here, equals 8.77. So that's the K. Then you move on to B. How much energy is needed to freeze this water? Right, so this is classic, what we've done twice already. So it's going to mass, change in temperature, C. Yeah. So to freeze the water, that just means that the C is going to go to 0 degrees Celsius, but it's going to complete the phase change. So mass times C times 0 minus 18, and that's going to give you this number here. And then, because this one's negative still, you have to minus this over here where it's mass times the phase change number here. And that's going to give you that, and then you sum the two, and that gives you the Q is negative 154,000. And remember, that's negative because from the water's perspective, you're taking heat out of the water. Okay. But then if you're looking at it from the freezer's perspective, you'll have to take the positive of this. C, how much electrical energy must be supplied to the freezer to freeze the water? Okay, so it's asking for the work, right? So, yeah, so Q, right, equals this over this. So what's work? Work is going to equal to the QC over K. We know both of those. We just calculated the Q, right? So this is QC because it's from the cold area, right? And that's what QC means. It's the heat that's taken from the cold area. So QC over K equals this. So that is the absolute value of work. And then, if you're still looking at it, yeah. So that's the energy supplied to the system. And then D, how much heat does the freezer expel into the room while freezing the ice? So what is QH? The heat expelled into the hot area, which is, in this case, the room. So you have, absolute value of W equals QH minus QC. So if you arrange that, QH equals W plus QC, this plus that, right? Of course, we just calculated that, this we calculated up here. So the heat expelled is 172,000 joules. So that is all for this recitation. I hope the paper was in line for most of the video and you were able to see what we were working on. If you have any questions, please feel free to let me know. I will try to get back to you, but I also have school, obviously. So hopefully this clears some stuff up, and good luck on your test.